Hey everyone, tonight we're going to look at what happens when something rolls down a hill, just like my friend Ben here. Okay, what determines the acceleration of Ben as he rolls down the hill? And as it turns out, we can describe this motion using Newton's second law, just like we've been doing for the past week or so. So, here we go. This type of problem is, I guess, officially considered a dynamics problem, okay? And we're going to ignore friction. So what I want you to do right now in your notebooks is I want you to draw a really, really big triangle, okay? Just like this. Here we go. This is a rough model of the hill that my friend Ben is going to be longboarding down. We're going to model Ben with a box. And of course, this hill has some sort of angle, theta, associated with it. So let's draw all the forces on Ben here as he rolls down the hill. Again, we're going to ignore friction, so we should only have a couple. We know that one of the forces that happens is a gravity force that points straight. Oh man. Is it? We know that there's a force of gravity that points straight down, because remember, gravity always pulls straight down. So we're going to draw a force vector right on this box going straight down. That's better. Let's label this vector going straight down as mg. Remember, that's equal to the weight. Also remember from last video that anything that rests on a surface has another force that's associated with it, called the normal force. Okay, now some of you may be tempted to draw the normal force straight up. But remember that normal in physics means 90 degrees, or perpendicular to the surface. So that means we're going to have to draw a force vector for the normal force going perpendicular to this surface right here. And again, we're going to label that capital N. So now we have a little bit different of a free body diagram this time. And we're going to have to use our tools that we've learned a little bit differently as well. So what I'm going to do is I'm going to set up a coordinate plane that's just a little bit different than what we've done before. Traditionally, we've made it so that y positive is up and x positive is to the right. Well, there's another way that we can do this that makes it easier on ourselves. So what we're going to do is we're going to take our normal coordinate plane and we're just going to rotate it so that the x-axis runs along the plane of our slope and that the y-axis lines up with the normal force. So I'm going to draw our new axis here in green, okay? So we'll have plus y going up and plus x going to the right as usual. But now this time we're going to have to use components. We're going to have to use vector decomposition to decompose our weight vector into two separate components. One of these components is going to be straight down. The other one of these components is going to go straight down to the left along the x-axis. Just like that. Let's redraw our free body diagram, get it away from the clutter of the triangle and the box and everything. Let's see what we're left with. Remember that this is the normal force, this is mg, and now we have to figure out what these components are. If you do your geometry homework, you'll recognize that this angle right here is actually equal to this angle right here. So we can fill this angle in as our theta. So if we go through SOHCAHTOA, we can find what these sides, these components of our weight vector are. So h is going to be our weight here. So this side is going to be mg sine theta. And if we go through again, that means this side right here is going to be mg cosine theta. Okay, so now we have all of these sides together. So what we're going to have to do next is set up equations for both the x and the y direction. Okay, let's do that on a new page here. Let's look at the x direction first. So we're going to sum up all of the forces in the x direction. So realize that Ben is rolling down the hill, so in the x direction it is a dynamic situation. Dynamic situation. So that means we have to set it equal to ma. Okay, this will be the mass of Ben and the acceleration of Ben. Okay, so now we have to look at, okay, what are all of the forces in the x direction? Well, let's go over here. We don't have any forces running up this axis up here, but we do have mg sine theta, the component of our weight, going down the negative x-axis. So we're going to write negative mg, and that's our sine theta, is equal to the mass of Ben and the acceleration of Ben. Okay, let's leave this equation for now. We're going to come over here and we're going to do our y case now. So let's decide if y is dynamic or static. So again, the y-axis is up and down perpendicular to the plane of the incline of the hill. So because Ben isn't going up the hill or down the hill, I mean he's going down the hill this way, but not down in the y-axis, this is going to be a static situation, and therefore we have to set it equal to 0. So we're going to sum up all of the forces in the y direction, and we're going to set that equal to 0. So let's look at all of the equations in the y direction. Well, we know we obviously have a normal force going up, but now counteracting the normal force, we have a negative mg cosine theta. And remember that all of this, the summation of all of these forces, has to equal 0. Now if we eliminate this 0, we get an equation that looks like n is equal to mg cosine theta. Okay, so now remember before when we had something sitting on a flat surface that the normal force was just mg. But now since we're on an incline, the normal force is less because it's just a component, just the y component of the weight. Okay? Let's come back over here to x. This equation probably won't tell us much. Maybe we could find the normal force. Let's go back over here because remember we're trying to find the acceleration of Ben as he rolls down the hill. So let's solve this equation for A. That's the mass of Ben too. Oh. Yep, that's right. The masses cancel. So this means that the acceleration of Ben, or I guess in this case, and in any case, whoever it is, the acceleration of someone going down the hill only depends on the component of the gravity, which depends on theta, or the angle of the hill. It doesn't matter what mass you are. It only matters... Let me just rewrite this to make it look neater. It only matters what the angle of the hill is. Wow, isn't physics cool?